In this video, we're going to look at two different forms of specific dipole-dipole interactions, the first of which is what we call hydrogen bonding. Not surprisingly, hydrogen bonding only forms between different polar covalent molecules that contain hydrogen. However, the other element in the compound can only be one of three elements: nitrogen, oxygen, or fluorine. This is not accidental because nitrogen, oxygen, and fluorine have three of the highest electronegativity values out of all elements on the periodic table. Nitrogen's electronegativity, being the lowest of the three at 3.0, is still significantly higher than hydrogen's 2.2. So if we do an electronegativity difference calculation, we see that this number comes to quite a high 0.8, considering that this is a covalent molecule. That means, in addition to, because nitrogen has a lone pair while hydrogen doesn't, that nitrogen is going to have a fairly strong negative pole because of how strongly it is able to pull the electrons in each of its bonds with hydrogen. And because of this, because these hydrogens are losing these electrons as they move away from it towards nitrogen, the positive poles that form on each hydrogen are also going to be relatively strong. Not as strong as what we see in water, however, because oxygen has an even higher electronegativity than hydrogen does. We can prove this by doing an electronegativity difference calculation to find that this comes to 1.2. In addition to oxygen having two lone pairs while nitrogen only has one, that gives it an even stronger negative pole, and again, because of its ability to pull the electrons in the bonds away from hydrogen, the hydrogens are also going to have quite stronger positive poles compared to the hydrogens in NH3. Fluorine, of course, is special because it has a higher electronegativity than any other element on the periodic table, and unlike oxygen and nitrogen, it has three lone pairs, giving it even more negative charge compared to the oxygen and nitrogen in water and NH3. We see that this fluorine, even though it's bonded to carbon, because its electronegativity is so much higher than any other element, we can see that this dipole is going to be even stronger than the other ones because of an even bigger electronegativity difference. That means that its negative dipole, or negative pole rather, there's only one, not two, is going to be stronger than the one on oxygen and water or the nitrogen in NH3. Now, because this negative pole is so strong, that means that it is naturally going to attract to a positive pole much more easily, which means that the attraction, the hydrogen bond that it forms, is going to be even stronger than another element that has a lower difference in electronegativity. For that reason, hydrogen bonding is considered the strongest form of dipole-dipole interactions because, again, of the large differences in electronegativity that each of these three elements makes between themselves and hydrogen, resulting in a stronger pole that forms and a stronger attraction that forms between themselves and the oppositely charged poles in similar molecules. Hydrogen bonding is important to study because of how commonly it occurs. Naturally, hydrogen bonding is most commonly found in water, which makes perfect sense because water has positively charged hydrogens bonded to a negatively charged oxygen, which allows it to form hydrogen bonds with itself in the form of other water molecules like this. This is important to us in solution chemistry because we're going to be looking at how water uses its ability to make hydrogen bonds and uses its polarity in order to act as a solvent. It's also very important to study hydrogen bonding because of the fact that hydrogen bonding occurs in many organic compounds such as DNA that we see up here and the protein structure that we see down here. Because a large amount of organic molecules contain oxygen, nitrogen, and hydrogen, hydrogen bonds naturally form within and between different types of organic molecules. The second intermolecular attraction that we're interested in this unit is what we call ion-dipole attractions. And the name pretty much tells you exactly what they are. Instead of forming between two molecules with dipoles, they form between polar molecules that have a dipole and ions instead. Again, this is very important for us because we're interested in what happens to ionic solids once we put them into water. And we can see, because NaCl is an ionic compound, because sodium has transferred its one valence electron to chlorine to give it a full outer shell, both sodium and chlorine have full positive and negative charges respectively. These are much stronger than any partial charges that occur within polar covalent molecules. So naturally, sodium, with its full positive charge, is going to attract towards the negative side on the oxygen in water, while conversely, a full negative charge in chlorine is naturally going to attract to the positive side of water, which is held in the hydrogen atoms in each of these water molecules. And each of these dotted lines shows the attraction between each of the ions and the oppositely charged pole in a polar molecule like water. This also applies to polyatomic ions like nitrate. We know that nitrate has a full negative charge, which is localized on each of the oxygens in nitrate's structure. Now, if each of these oxygens has at least some negative charge, that is naturally going to attract to the positive poles that we see on each of the hydrogen molecules here. And because nitrate, again, has a full negative charge, that means that this is not just an attraction between two polar molecules, but between a polar molecule and an ion with a full charge. In the final video in this series, we're going to look at the different interactions that are formed between nonpolar molecules, which again are molecules that do not have a permanent negative or positive side the way that water, ions, and other polar molecules do.